So complex numbers has always been one of my favorite topics in mathematics. And I love all the stuff that you can do with them, but one of the things I've always had a difficult time visualizing is what happens when you square a complex number. Not take the complex conjugate and multiply by it, meaning take the modulus square, but actually square the complex number. If you do out the algebra, you get out a real part that's equal to the original real part squared minus the original imaginary part squared. This is why it's possible to square a complex number and get a negative real part. And then the imaginary part is the cross term. It's 2 times the real part times the imaginary part. So what I've done here in GlowScript is made a function to kind of help me visualize that. This function square a complex number with a real part and an imaginary part. And so we return the real part as the x component of a vector and the imaginary part as the y component of a vector, because that's what you do to represent complex numbers in the complex plane. You make the real part the x component and the imaginary part the y component. Now, to help visualize that, we're going to create some arrows. The way these arrows work here down in this loop is that each arrow is going to start at the number that we're squaring, and it's going to end at the number that is the squared complex number. So here we set up our start position. We start with the value of x and y, and then here we square that complex number, so you're using the function we made earlier. Now, the way arrows work in VPython is that you set their position and then you set an axis. An axis is the end point minus the starting point. So over here I have the end point, here I have the starting point. And then this part with the red and green is just to help us be able to visualize them better. So this is just keeping track of how red or how green to make the arrow that we're looking at. And so we're going to make these arrows in the complex plane. They're going to start down at -2, -2, and work their way up to the opposite corner. And we're going to increment in steps of 1. So I've got 2 loops set up here. We'll loop over the real part here with the x value, loop over the imaginary part here with the y value. And when we press Control 2, we get this nice visual, and I think this kind of helps me get an idea of what happens when you square a complex number. By the way, the red dot here in the middle is the origin, just so we can keep track of where everything is. So this is 0, 0. Obviously, when you square 0, 0, you're going to end up back at 0, 0, so that's fine. But this shows me, for example, that my traditional concept of squaring a real number, produces a positive number. So when I square a pure negative number, something with a negative real part and 0 imaginary part, it zips over to this side of the origin. It gives me a positive number. And of course, anytime I square a positive number, something with a positive real part and no imaginary part, or 0 imaginary part, it zips farther along the real axis here. So everything along the real axis goes into the positive semi-axis over here. But all the other stuff acts a little bit more interesting. For example, here I've got a positive real part and a positive imaginary part that are equal by the looks of this 45-degree angle here. That ends up here being a pure imaginary number, because all I have left is the cross term, because when I take real squared minus imaginary squared, those are going to cancel, and I end up with something over here. Same thing happens over here when I'm in quadrant 3. When I have negative real, negative imaginary, the number jumps up here to be a pure imaginary number. And then, of course, I can have the same thing happen in the quadrant 2 and quadrant 4. I can have my squared number end up being a pure imaginary number, just being a negative imaginary part down here. But then this part's neat because I can kind of connect these arrows. So for example, if I start along this axis, I end up over here at a negative number, because whenever I square this negative imaginary number, I end up with a negative number over here. So you can imagine starting over here, you jump this way, you jump this way, you jump this way. It's kind of cool to see. And then of course, when you have these scenarios over here where it doesn't match up, like when the real and imaginary parts aren't equal to each other, you end up somewhere else in the complex plane. So you can use this to play around with, get an idea of what squaring different combinations of complex numbers produces. Let's try changing this a little bit. Let's up this to 4. So we'll go from -4 up to but not including +4. That, of course, makes it a little bit messier, but it makes the pattern a little bit easier to see. The color looks amazing on this view, I think. So you end up with kind of this void over here. You have things starting out but not going into this region, which is kind of cool. And things just kind of keep going out and kind of spiraling out. Because, of course, as you're squaring it, the magnitude is generally going to get bigger for most of these numbers that we are working with. But it gives you these nice, pretty combinations here. Now, I mentioned before, following some of these arrows around with these different trajectories, that's actually the whole idea behind what's called the Mandelbrot Set. The way the Mandelbrot Set works is that you start with a complex number, so let's call it our starting complex number with a real part and an imaginary part. And then you take that number and you square it, just like we're doing in our function here. But this time you add on another complex number. It's usually called C. And the Mandelbrot set is the set of all complex numbers C, where you can repeat this process of square and add C, square and add C, square and add C, and the results don't diverge. They don't go off to infinity somewhere, that they stay bounded. And so it's this process of checking this over and over again that we'd like to be able to visualize. And so that's what I've set up in this loop here. Basically, you specify the number of iterations you want to check. In principle, you have to do an infinite number of iterations, but maybe you can get away with 10, right? 10 is approximately infinity in some cases. And so we start out with a real part and an imaginary part, and then we take that complex number and we square it, just like we did before, and we're going to add this complex number C. So this C stays constant throughout. The starting point changes. Notice I update the starting point down here to be wherever I ended up before. And basically what we're going to do, we're going to create arrows that go from that starting point to the stopping point. And if C is in the Mandelbrot set, then this thing should converge down within some range. And if it's not in the Mandelbrot set, then the thing will run outside and diverge to infinity. So let's see what happens. Let's hit Control-2 to run. So this is actually animating now. We're going to do one arrow at a time. So you see we start out with our original point here, then this becomes our next new point, and you can see the arrows are getting squishier and squishier until finally they basically have 0 thickness down at the end there. That's looking like that's going to converge, and in fact I checked that number earlier. It is in the Mandelbrot set, so it does work out that way. Let's try taking one that's not in the Mandelbrot set. So let's take, for example, 2, 2, and let's hit Control-2 to run. So here you can see the arrows get longer and they're pointing farther and farther away until GlowScript can't even render the arrow shaft anymore. We just get the arrow head, and yeah, that's not working. Oh, and in fact we reached infinity. All right, that's definitely diverging, so that's definitely a problem. Let's try just a couple more. Let's try 1, 1. So this is 1 plus I. Let's see if that's in the Mandelbrot set. Does that result in a convergence or a divergence? That's looking pretty divergent. Yep, that's pretty divergent there. Okay, let's try smaller. Let's try a half and a half. Control-2. That's getting pretty divergent. Okay, let's see if we can get one more that's in the Mandelbrot set. Let's try, let's just go for small numbers here. Let's try 0.1 and 0.1. Control-2 to run. And there we go. This one's taking a little bit different direction than our first one, but the important thing is that the length of those arrows is getting smaller and smaller. And in fact, ooh, they're actually just looping around each other there. That's pretty cool to see. So anyway, these are a couple of fun codes to play around with, help you visualize complex numbers. Hope that's helpful to you. Thank you so much for watching. I will see you next time. Bye-bye.